When we talk about the overall shapes of molecules and the shapes of atoms, we find that we can't use the shapes of pure orbitals to explain the shapes of molecules. So if we were just to use these p orbitals, for example, then what we would find is that this doesn't explain a trigonal shape, for example, because the trigonal shape would have atoms that would point down here or point down here away from the directions of any of these orbitals. The only way that we can describe or use these orbitals is if we employ the concept of hybridization. So here's an example of what I'm talking about with hybridization. When you've got carbon, you've got 6 electrons you need to put into an electron configuration. You'll start off with 1s, 2s, and then have 2p up here. You'll have 2 electrons you'll put in here, 2 electrons you'll put in here. That's for 4, this would be 5, and this would be 6. And in order to explain the tetrahedral shape of something like methane, what we would find we would need would be 4 hybrid orbitals, that is 4 orbitals of equal size and length. Presently, if we go back over here, you've got 4 orbitals, but they're not the same, and they all have different directions, all different sizes, and all different lengths. And what we need is 4 orbitals that are made up of these that actually fit the bill. So what we do here is we take the s orbital and 3 of the p orbitals and we mix them together. And here's an example of that. If we pretend that the s orbital is blue and that the p orbitals are green, and we mix all of these 4 together, what we're going to get is a mixture of blue and yellow, which is green. Now this mixture is going to be completely equal, and then we take these 4 shot glasses, if you like, and we pour the green back into each of them, and what we end up with is 4 hybrid orbitals. And each of these hybrid orbitals is made up of 1 part s and 3 parts p. Think of this as being like vodka and orange juice. Vodka and orange juice, and this here would be a screwdriver. And what we're doing here is we're mixing the vodka and the orange juice, and then we're pouring the screwdriver back into the 4 glasses that we made that the orange juice and the vodka came from, and that gives us 4 equal drinks as opposed to 1 drink that was different and 3 that were the same. And this gives us 4 equal or hybrid sets. So an sp3 is made up of 1s and 3 p's, and it gives 4 separate sp3 hybrids, each made up of 1 part s and 3 parts of a p orbital. Well, let's take a look at what an sp3 hybrid looks like. And here's what we would do. If we've got methane, for example, which is CH4, what we would do is we'd end up with 4 hybrid orbitals, which would be the result of mixing 1s and 3 p's together to give 4 sp3 hybrids. And here's what an sp3 hybrid looks like. As you can see, it looks mostly like a p orbital because it's mostly p, but it does have a little bit of s character about it as well. It's a little bit fat up the top, which accounts for the s part of the sp3 hybrid. Alright, well, let's see how we can use these hybrid orbitals to explain shapes of molecules. So let's say we've got something like methane. This is CH4, and what I'm trying to show here is that these 2 hydrogens are in the plane of the screen. This one is pointing back, and that's what the dash means, and the wedge here means that this hydrogen is pointing forward. The shape I'm trying to present here is called tetrahedral. So what we've got around carbon is 4 groups, and these groups all have the same bonds and the same bond lengths. That's why we need 4 equal hybrid orbitals. 1s and 3 p orbitals by themselves will not explain this shape, but 4 sp3 hybrids pointing in a tetrahedral array will definitely explain this shape. If we've got 4 groups, that means we need 4 hybrids, and 4 hybrids will have to come from the hybridization of 4 different orbitals, 1s, a p, and a p, to give 4 sp3 hybrids. So the hybridization of methane is going to be sp3. I'm going to go back here and show you this again with the mixing of the orbitals to give the hybrid orbitals. And as you can see, to get these 4 sp3 hybrids, what I had to do was mix 1s and 3 p's together. Now I know I needed 4 because I've got 4 groups, and if I need 4 hybrids I need to mix 4 orbitals to get those 4 hybrids. Alright, let's go back to the diagram I was showing you. Let's say we've got this compound here, which is called formaldehyde. It's got 3 groups attached to the carbon atom. I know there's 4 bonds, but we're only talking about groups attached to the carbon atom. And what we have here is 3 groups. If we've got 3 groups, it means we need 3 hybrids. If we need 3 hybrids, it means we need 3 orbitals to make up those hybrids. And what we would do is we'd mix an S, a P, and a P. And what we'd end up with is 3 sp2 hybrids. Alright, going back to the original diagram here. In order to get these sp2 hybrids, what I did was I mixed one s and then 2 of these p's, and we have a p orbital left over. So what we end up with is 3 sp2 hybrids with a leftover p orbital that is actually involved in one of the double bonds to the object. Alright, so you've got 3 sp2 hybrids, and one of these double bonds is that leftover p orbital. But we've got 3 groups, 3 hybrids. We need an S, a P, and a P to get 3 sp2 hybrids. Let's say we're looking at this compound now. This is called acetylene, and we're looking at this particular carbon atom. It has 2 groups connected to it. That means we need 2 hybrid orbitals. To get 2 hybrid orbitals, we need to use 2 orbitals. We'll use an S and a P, which will give us 2 sp hybrids. So the hybridization of acetylene is going to be sp. Alright, let's go take a look at another couple of examples, a little bit more complicated now. Let's say we've got this compound here, which is SF4. It's got 5 groups around it. Remember that the lone pair is a group. It takes up space and needs to be accounted for in the hybrid orbital structure. We've got 5 groups around the central atom of sulfur. That means we need 5 hybrids. So what are we going to use? We're going to use this S, a P, and a P. Now remember, there's only 3 p orbitals, so now to get another hybrid we're going to have to jump up and take a d orbital as well, and we're going to end up with 5 sp3d hybrids. Alright, so what we've done here is just used the 3 p orbitals and then jumped up and took another d orbital to get the 5th hybrid out of that. So sp3d. So each hybrid orbital is 1 part s, 3 parts p, 1 part d. With this one here, we've got XeF4. We have 6 total groups. That includes 2 lone pairs of electrons and 4 atoms. 6 groups means we need 6 hybrids. 6 hybrids would come from 6 orbitals. 1 s, p, 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 d, and d. So we need 2 d orbitals here to make up the rest of the hybrid. So we've got sp3d2, and that would be for an atom that had 6 things around it. All of this is summarized in this table here. And you can see it here that the hybridization will be defined by the overall shape, which will indicate the total number of groups around the central atom. We always need as many hybrids as we have groups, and the hybridization then will be predicted by the number of hybrids. So if we needed 2 groups, that means we need 2 hybrids. We need an S and a P to make up 2 SPs. Trigonal, we need 3 groups, which means we need 3 hybrids, and the hybrids would be made up of 1 S and 2 Ps. The hybrids need as many orbitals to make them as they have orbitals involved in them. So if you've got an sp2, that's 3 orbitals, which comes from an s and 2 p's to give a total of 3 orbitals, which gives 3 sp2 hybrids. And you can see the tetrahedral will be sp3, which comes from 1 s and 3 p's, and that's a total of 4 hybrids to give 4 sp3 hybrids. sp3d is made up of 1 s, 3 p's, and a d. That's a total of 5, which gives 5 sp3d hybrids. And then 6 is going to be made up of 1 s, 3 p's, and 2 d's to give 6 sp3d2 hybrid orbitals.